of this, the shaking earth, and you can already see this in the background. I start with a few classical earthquake, let's say, impressions. So if you look at this one photo, that is San Francisco in 1906. That was the big earthquake that basically destroyed the city. It was magnitude 7.7 to 8.3. You see there's already a large variation in there for the simple reason that at that time we did not have very good recordings to basically be able to accurately determine magnitude as we are today. And San Francisco was a classical case in a sense. I mean, California, a major earthquake country, as you will see in a couple of next slides. And the key destruction though in San Francisco was not necessarily the earthquake shaking itself, but the fires that ravaged the city afterwards. So you had gas leaks and you had fires developing, growing into super congregations and basically burning down virtually the entire city. Then here, an event that also, of course, was very, very devastating and dramatic was the Haiti earthquake in 2010. I don't know if all of you remember this event. It was a magnitude 7 earthquake. As such, not yet of the highest strength, as you will see, from the magnitude level, but extremely devastating because it was very nearby the main settlement Port-au-Prince, and because also of the building practices. Here you see basically an image from one of the poor quarters of the city, which were built in very steep slopes without proper construction practices and nothing, and these basically just were completely destroyed, were slipping literally away. And this is just another image of a landslide. Oops, you can see this. And this event caused more than 200,000 casualties, so it was an enormously devastating event. This is now an event which is in the scientific community very, very interesting, and which was also very devastating, but on a different level. So this is the Christchurch event in 2011. You actually had a bigger earthquake before the Christchurch event, which is the so-called Darfield earthquake, which had magnitude 7. But this earthquake was not directly underneath the city and didn't cause much damage in principle. But the Christchurch event was really, literally directly underneath the business district of Christchurch. Had only a magnitude of 6.3, but destroyed virtually the complete business district. Caused lots of phenomena that we call liquefaction, for instance, where the soil literally liquefies and gets and basically flows away. And here you see a photo taken during the earthquake. So really the developing of the cloud there. And this is one of the major office buildings that collapsed. And so here you had about, 180 casualties to my memory, but also huge economic losses. And then this is of course an event that also remains very strongly in our memory. Also from 2011, the Great Japan earthquake, magnitude 9, Tohoku earthquake. And here you can see the incoming tsunami at the coastline. So these are a few of these classical devastating earthquake impressions. And to better understand this, just a brief reminder of coming back to plate tectonics, which probably most of you have seen in the basics in geography classes. So basically on the right-hand side, you see a kind of sketch with the major tectonic plates of the Earth crust. So the Earth crust is composed of a certain number of tectonic plates, around roughly a dozen major plates, and then quite a few smaller ones. So here, for instance, you see the Pacific plate, you see the African plate, here you see Eurasian plate, where we are located in the center of it, not in the center, but well away from the boundary. And most of the earthquakes, when you look at the map on the left, so this is the catalogue of earthquakes from until 2008, if I see that well, again, and also here. And so basically, these are color-coded with depth, so the red ones are the shallow ones, and the green ones are very deep earthquakes. And so what you can see is that the earthquakes are very nicely distributed, mostly along the plate boundaries. So that's where the major part of the shaking and of the earthquakes are occurring. You also have earthquakes that occur very, very deep, at up to 700 kilometers depth, which are actually physically not so easy actually to understand why they can occur, because normally earthquakes occur in a brittle crust, so basically you have a displacement of 2 blocks of crust along a fault line, but if you go that deep, it gets hotter, and when it gets hotter, your material gets ductile. So your material should not actually break in the same way as it breaks closer to the surface. And so there are lots of theories about these and lots of discussions, but that is still a matter of ongoing research, why you actually have such deep earthquakes. So, as I said, so you have at some plate boundaries, like in California, you have the plates moving alongside of each other, so just horizontally. You have other areas where basically new crust is generated, which is mostly along the mid-oceanic ridges, so where the plates diverge from each other and where you generate new material. And then you have plate boundaries, like for instance here in South America, or also in Japan, the so-called ring of fire, where basically one plate is diving underneath the other and being removed again. So
we can measure the change in the atmosphere. So we measure that from all the stations around the world. And so we're about 1.9 parts per million per year is the change in the atmosphere. And we can multiply it by the mass of the atmosphere to get the mass of CO2 that changes each year. And that's about 17 gigatons of CO2. And we know what the amount is emitted from fossil fuels. So we have 34 gigatons that are emitted from fossil fuel combustion. We have a little bit from land use change. And if we subtract the amount in the atmosphere, we actually realize that there's a difference of 22 gigatons of CO2. So where is this going? Well, actually, the CO2 is also removed from the atmosphere by natural processes. And these are removing nearly 50% of the CO2 that's emitted. And so this CO2 is going into the so-called land biosphere. That's when plants take up CO2 through photosynthesis. They produce carbohydrates, and that's stored in the plant matter. And it's also some of it stored below ground in the soil. And that accounts for about 52% of the sink, or the removal of CO2 from the atmosphere. And then we have the oceans as well. So the oceans also take up CO2 from the atmosphere. And that's just simply a process of equilibrium with the water dissolves CO2. The water is very good at holding CO2 actually, and forms bicarbonate in water. And then also you have all the phytoplankton that live in the ocean, and they also carry out photosynthesis. So they also take up CO2, convert that to carbohydrates, and then this is then when these phytoplankton die, they fall to the lower ocean, to the deep ocean, and it's also where carbon is then stored for the long term. So that's also a removal process of CO2 from the atmosphere. And there's a little bit of uncertainty in these numbers, but we know fairly well that the balance of this. So an interesting fact is that even though the emissions of CO2 have been increasing, so from year to year over the last more than 50 years, the fraction of CO2 that's remained in the atmosphere has been quite stable. So that means that the sinks have been increasing in pace with the emissions. And I think that's quite remarkable that the ocean and the land biosphere are actually increasing their uptake of CO2 more or less in pace with the emissions. So that the fraction of CO2, so the fraction of what's emitted, that stays in the atmosphere is quite stable over time. It has been increasing slightly by about 0.25% per year, but over the last more than 50 years it has been quite stable. So from what I've all just said in the last few slides can be summarized in this figure. You can see, actually, maybe I'll show you the pointer. So on, we have a zero line here, and you have the emissions on the positive side. So that's land use change and fossil fuel going up over time, now reaching about 40 gigatons. And in the negative side, you have all the sinks. So that's the ocean sink, the land sink, and the change in the atmosphere. And that balances, you see that's also, so the total source is about 40 teragrams of carbon dioxide. And then you have the total sink, which is balancing. And but you see also in the sinks, there's a lot of variability from year to year. That is determined by the land sink, which is changing due to climate variability. So you may have heard of, like, for example, the North Atlantic Oscillation or the El Nino Southern Oscillation. These are so natural climate variability, which means that some years you might have like hotter, drier summers, and other years maybe warmer, more mild winters. So all these natural climate variations also mean that the land sink of CO2 is also changing. So how do we know this? I mean, how do we know where the CO2 goes? And so in the next few slides, I'll show you a bit about how we know where the sources of CO2 are coming from and where they're going. So I'm going to start with radiocarbon. So this is what we call carbon-14. I'm not sure if you have come across, maybe in your physics or chemistry classes, the idea of isotopes. So if you have an atom, for example, a carbon atom, they can be different or variations. So an atom is determined by how many protons it has in its nucleus. So carbon has 6 protons, and carbon-12, which is the most common form of carbon, has 6 neutrons. But you can also have a form of carbon which has 8 neutrons, and so we call this carbon-14. And carbon-14 is formed in the upper atmosphere by a reaction with nitrogen-14 with a neutron, and it produces carbon-14 plus 1 proton. So carbon-14 is a little bit radioactive, and it will decay with a half-life of 5,700 years approximately. And we can see it in the atmosphere in this figure. Actually, carbon-14 was also produced from nuclear weapons testing in the atmosphere in the late 50s. So actually carbon-14 went up in the atmosphere, and now it's starting to decay because it's a radioactive decay, but also because of fossil fuels, which I'll show in the next slide. So we have carbon-14 that exists in the atmosphere, and that reacts with oxygen to form carbon-14 CO2. So we have both carbon-12 CO2 and carbon-14 CO2, and these are both taken up by plants to make carbohydrates. So we have, so here's a leaf. It takes up CO2 through photosynthesis, and that includes both a little bit of carbon-14 CO2 and a bit of carbon-12 CO2. And when fossil fuels, they are basically through heat and pressure over millions of years, the organic matter is then converted to fossil fuels. And over that time, of course, all the carbon-14 decays to carbon-12. So in fossil fuels, there is no carbon-14. It's only consisting of carbon-12. So when you burn fossil fuels, you only emit carbon-12 CO2. So actually, when you burn fossil fuels, you dilute the amount of carbon-14 CO2 that's in the atmosphere, and we can actually measure this. So we have a decay of, so we have anyway a decreasing carbon-14 CO2 in the atmosphere after we stopped nuclear weapons testing. But we know how much that is just from the lifetime of from carbon-14. But then we have an additional contribution, which is from fossil fuels. And so we can actually use the measurements of carbon-14 to see how much fossil fuel has been emitted. So that's quite a good check. We have the statistics of how much like oil and coal and gas is produced and how much is used for energy production. But then we can also measure this in the atmosphere by looking at carbon-14.